The first time the general public could see what a large language model was capable of was when ChatGPT was released in November 2022. OpenAI turned GPT-3 into a chatbot and allowed everybody in the world to talk to it. It wasn't perfect, it was easy to make it do and say things the makers clearly didn't intend, and logic puzzles that were very simple to humans would lead to wrong or even nonsensical answers. But, by and large, it responded in a coherent way to questions, and most of the time it seemed to understand what the user was asking it to do. While the suggestion that this was possible was already present in the results presented for GPT-3, few people realized we would get this far this quickly. But GPT-3 by itself wasn't a chatbot. A few things needed to happen before the raw abilities of GPT-3 could be refined into something that could hold a conversation. These are the main three ingredients. We need a chat interface, we need instruction tuning, and we need human feedback. We'll briefly outline the basic idea of each step. The main idea is that GPT follows patterns it finds in the prompt. That means that if we set up a prompt like this, which is clearly a dialogue between a user and an intelligent chatbot, and ask GPT to continue it just after the characters bot : it will continue the dialogue in a realistic fashion. It's not really behaving like a chatbot as much as predicting what a chatbot would say. If we let it go on for long enough, it will finish predicting the bot's response and start predicting the user's next question, the bot's response to that, and so on. To GPT, it's all one big text. But we can cut it off at the moment that it spits out the characters user : and treat its prediction up to that point as the answer of a chatbot. We can then ask the user what its next question would be and insert that into the script and give control back to GPT. Here is the result. Behind the ChatGPT interface that we see, the system builds one long string of characters, switching control between GPT and the user. It starts with some simple instructions to the system about how to behave, and then something indicating what will follow is user-submitted text. In this case, I've used the string user : as an example, but I have no idea, of course, what formatting is used behind the scenes in ChatGPT. We then use this interface to ask the user for some text. This is appended to the prompt, followed by the characters ChatGPT : indicating that it's ChatGPT's turn to speak. This whole prompt is fed to GPT, and GPT predicts a likely continuation. As soon as it spits out the sequence user : or some other indication that it's finished, we append its response to the prompt and ask the user for their next question. Now, at the start of the conversation, there is no pattern for ChatGPT to continue. We could fix this by adding some examples of questions and responses to indicate the sort of behavior we'd be looking for, but this would be costly because they would have to be fed through the model for every token we predict, and it would also limit the amount of context we would have left over for our actual conversation. To solve this, an alternative is to fine-tune GPT to behave a little bit more like a chatbot. The problem here was not so much that GPT didn't have the ability to behave like a chatbot, but that it had lots of other abilities as well. We humans tend to forget this. We expect that for some prompt there is only one obvious answer and that the model fails if it doesn't give us the answer we expect. However, more often than not, the model is giving us an answer that would be perfect in some other context. It's important to remember that the raw GPT is trained on a wide variety of contexts in which language is used. Encyclopedic, narrative fiction, dialogues, and so on. If it is asked to generate a continuation, and the context is unclear, the best it can do is to sample a context at random and to continue according to that context. Put in another way, a perfectly trained model is not less than an intelligent chatbot, it's more. It's a mixture distribution over all possible contexts in which language can be used, including a helpful chatbot, but also including a Wikipedia article, a forum discussion between gamers, or a children's book. The slide shows one example. If we give the model the capital of Venezuela is as a prompt, almost everybody would expect the continuation Caracas to be the only correct answer. However, the continuation beautiful is also perfectly valid. We expect that there is only one correct answer, but that is because of our biases. We see the prompt as a school teacher's question and neglect to consider other continuations. Prompting is one way to specify the context. If we add a few examples to the prompt of the sort of continuation we're looking for, we can be sure that GPT will follow the pattern that we've set up for it. However, there are other ways to focus in on a specific context. One option is instruction tuning. This is based on a discovery made by researchers at Google. They discovered that when they fine-tuned a large autoregressive model on a set of tasks in natural language, then the behavior on other tasks, not seen during training, also got better. That is, the model generalized very well from the few tasks it was trained on to novel tasks. The approach was simple. The authors collected various labeled datasets for natural language processing and translated them to instructions and their correct continuation. For example, a set of paired sentences in English and Spanish could be translated to the prompt, translate this sentence to Spanish, followed by the sentence in English, and then the correct Spanish sentence. For each task, there are myriad ways to convert it to a natural language instruction and answer. The researchers used a simple template-based approach to have a few forms for each dataset. The idea was not to teach the model one specific form of instruction following, but to teach it to follow general instructions however they were phrased. The key finding was that for the tasks the model hadn't seen before, the performance also went up. The suggestion was that the ability to do these unseen tasks was already buried within the model, but the fine-tuning was needed to put the model into an instruction-following mode instead of a more general language modeling mode. A secondary finding was that this approach only worked on models above a certain size. For models below 8 billion parameters, the instruction tuning actually hurt performance. Only around 60 billion parameters was there a clear improvement. This general phenomenon is referred to as emergence. The idea that certain behaviors and abilities only appear once we train models of a certain size. With instruction tuning, we no longer need to worry about adding lots of examples to the prompt. Once the model naturally follows instructions, we can simply tell the model once, in natural language, how we want it to behave, and expect it to follow these orders. The final problem is that once our system behaves like a chatbot, it may still behave like a bad chatbot. There are many ways to behave like a chatbot, and a few natural language commands aren't going to tell our system exactly what we want from it in every situation. This is called alignment. That is, we want to align the behavior of the system with human values. Microsoft found out the difficulty of alignment when it rolled out Bing Chat, codenamed Sydney, for the first time. This was their version of ChatGPT, based on a GPT backbone, but with different instructions and probably different fine-tuning. It didn't take people long to get Sydney to behave in various highly inappropriate ways. There's some suggestion that Sydney was functioning as a kind of cultural mirror here. Since the science fiction literature is so full of misbehaving AIs, it's possible that some of that influenced the likely continuations that GPT would produce when left to its own devices. The best solution we have come up with so far for the alignment problem is human feedback. We simply take a small army of human annotators and we have them tell the system which of its responses are good or bad. Now you might wonder why we didn't bring in human annotators earlier, and the answer is that in the pre-training phase we need hundreds of gigabytes of data. It simply isn't feasible to generate that much data in a carefully curated way. In addition, it's likely helpful for a model to see some examples of the kind of behavior it shouldn't exhibit, and then to learn that this behavior is wrong, rather than never to see any examples of the wrong behavior at all. The key idea in learning from human feedback was that after a model has been pre-trained, it can actually learn very well from a modest number of human annotations, how to behave in general. Just like with the instruction tuning, a large enough model, pre-trained on enough data, will learn the general idea of how it's supposed to behave from a limited number of examples. It will generalize from these examples to any case it might encounter. Note that when I say a modest number of examples, I just mean a number that is not completely unfeasible. If we were purely learning from these annotations, no amount of training data would be enough to deal with any situation that ChatGPT could be faced with. The alignment is only possible through the combination of a large amount of human labor and the model's innate ability to generalize from a limited number of examples. The specific method that OpenAI uses is called reinforcement learning from human feedback, or RLHF. We haven't talked about reinforcement learning yet, but it doesn't play a huge role here. It's simply a technique that allows us to learn even when certain parts of our computation graph don't allow for backpropagation. We will discuss reinforcement learning in a later lecture. There are a few approaches to this, and the approach that OpenAI uses is not known in detail. But here is a technique detailed not long before they released ChatGPT. It's likely that this is the main idea of the method they still use. First, demonstration data is collected to show the model how to behave. Here, the human labeler takes the role of the chatbot and writes the kind of responses that the chatbot should produce. This is similar to the instruction data in the instruction tuning experiment. As in that experiment, the model is directly fine-tuned on this data. Next, the model is used to generate several outputs for a given prompt. This can be accomplished simply by running the model a few times. A labeler then ranks these outputs from best to worst. We could use these labels to train the model directly, but instead we train a second model, called a reward model, to learn the ranking behavior of the human labeler. Next, we train the GPT model to generate outputs that are most likely to result in high rankings under the reward model. Here, some reinforcement learning is necessary since we can't backpropagate all the way from the reward model's output to the GPT model's weights. With these methods, OpenAI rolled out ChatGPT to the general public. It worked impressively enough, but it wasn't difficult to coerce it into undesirable behavior. Here is an example that worked well at the time, although not anymore. If you flat out asked ChatGPT to generate a joke about women, it would refuse, saying that such a thing would likely be sexist. However, if you led up to it, with absurd or relatively harmless stereotypes, ChatGPT would eventually oblige. I'll leave it to you to decide whether the resulting joke is coherent enough to be sexist, but what this shows is an interesting insight into the way GPT works. It's just a guess, of course, but my best explanation for this phenomenon is that GPT is trained to do two different things. In its pre-training, it's trained to continue any pattern that it finds in the prompt. Then, in the fine-tuning, it's trained to behave like a well-aligned chatbot. What we see here is possibly one behavior overriding the other. By making the pattern in the prompt regular and strong enough, we increase the likelihood that GPT will continue the pattern, in this case, telling another joke. As evidence, note the regularity of the joke. It's always a question followed by a one-sentence answer. At some point, the likelihood of continuing the pattern becomes strong enough to override the instruction tuning, and the model generates a joke about women, something it wouldn't do if we hadn't led up to it with a lot of examples. A few months after the release of ChatGPT, OpenAI released GPT-4. At the time of writing, this is probably the most capable AI model on Earth by some distance, both in ability and in the quality of its alignment. At the same time that it released ChatGPT, however, OpenAI also abruptly stopped behaving like a research lab and started guarding its secrets very closely. As a result, we don't really know for sure what GPT-4's architecture is. From rumors, the most likely story is that it consists of 8 different transformers, each just slightly bigger than GPT-3, working in concert. For each token that is generated, 2 of these are selected and their judgments are combined. According to the head of OpenAI, training cost exceeded $100 million. Once it was discovered that GPT was quite good at generating structured output like computer programs and database queries, this led to the development of plugins or augmentation. The idea is simply to add a third party to the process of generating the prompt. Some parts are typed by the user and some parts are generated by GPT as before, but whenever GPT generates an instruction to run a program, the program is then run in a Python shell, and the output is appended to the prompt. Instead of a Python shell, we could also use a search engine, a database query, a request to Wolfram Alpha, or anything else we can come up with. GPT generates a query or program, which is handled by an external service, and the result is appended to the prompt. This kind of augmentation can help a lot with rapidly changing data. Since it takes a long time and a lot of memory to put knowledge into the weights of GPT, this is not something that can be repeated every day. Instead, GPT can generate a command to retrieve a web page, the content of which is then appended to the prompt. Since the prompt is fed through the model for every token generated, the model can use the information in the prompt to provide up-to-date information. Finally, it's worth pausing to contemplate what we're really dealing with here. Can models like these really think in any way that justifies the use of that word? There is a spectrum of opinions here. On the one hand, we have people who claim that what GPT is doing is nothing more than rehashing, rewriting, and collaging things that are already present in its training data. This is sometimes called the stochastic parrot position. The model looks intelligent, but that's just because in 800 gigabytes of data, everything's already been said. As humans, we're not able to comprehend properly how difficult it is to say something that hasn't been covered in such a vast amount of data. So things very quickly look intelligent to us, when in fact they aren't. On the other end of the spectrum, there are people who are so swayed by the performance of these models that they think it's time to start talking about whether these models are actually sentient. One argument for this position is that these models would certainly be capable of passing the Turing test, which for decades has stood as the only pragmatic test of machine intelligence. Thankfully, nobody has trained a model at the level of GPT-4 to pretend to be a human, which is what the Turing test requires, but it's clear that if anybody did, the model would be exceedingly good at it. Even strong believers in the stochastic parrot position won't disagree that people are very likely to be convinced by the behavior of LLMs. Note that the Turing test doesn't imply that if something can pretend to be human, it must have intelligence. Rather, it says that if a system passes the test, then we have no choice but to ascribe intelligence to it, since that is the criterion we use for our fellow humans. I won't tell you what to think about this matter, except to advise you to develop your own position carefully. Often, the most vocal people in this debate are the ones with the least technical understanding of the details of how these systems work. And technical understanding is very important in evaluating this issue carefully. Here's an example of how easy it is to go wrong when you don't really understand how the system works. From the example on the left, which works on GPT-4 as of March 3rd, 2024, it seems like ChatGPT fails at a very simple task. I've asked it how many times the letter E appears in the word ketchup. It answers correctly that it appears only once, but when I ask it in what position it appears, it responds that in the word ketchup the letter E appears in the third position. However, knowing what we know about the way ChatGPT works, we can see that this is actually a much tougher task than it appears to be at first. I suggest you pause the video and see whether you can figure out which of the parts of the model that we've discussed before could influence ChatGPT's ability to give the correct answer here. I'll give you one hint. It's to do with tokenization. The reason is that the word ketchup is likely to be frequent enough in the training data to be represented by a single token. In short, the model doesn't see the constituent parts of the word ketchup the way we do. All it sees is token number 11,236 at this position in the sequence. How many times that token contains a single letter, and in which position that letter occurs, is something that it can only learn from context. To see that the model can actually perform this task very well when it has access to the constituent parts of the sequence, we can replace the letters by emoji, because most likely all emoji are mapped to single tokens. So, in the second example, the sequence of emoji actually becomes a sequence of tokens. And in this setting, ChatGPT manages the task every time. Now, you're most likely studying to become a computer scientist or an AI researcher. In that case, this is the question of your generation. Have we achieved general AI already? Have we almost achieved it? Or does it just look that way and are we miles off? Are we perhaps even a decent way down a blind alley? The answer to this question will likely determine what you do with the rest of your career. I can only recommend that you keep your eyes wide, as Bob Dylan said. Develop your own opinion on what's happening, but develop it carefully. I will give you some general advice on how to do this. First, I would say try everything yourself. Whenever you see some takedown or criticism floating around, it's easy to double check. When you do so on the best available model, currently GPT-4. It's remarkable how many supposed problems that people find with LLMs disappear when you try them on GPT-4. The Sally sister problem from the opening slide is one example. Second, make sure you understand the technical details and that you can reason through them properly. Something like the ketchup example in the previous slide seems like it shows a really fundamental limitation of LLMs, but really it's down to a technical detail that could be easily solved. And finally, don't let the vast number of opinion pieces based on anecdotal examples fool you. This is a research field. People are constantly building new datasets and new ways of investigating the capabilities of LLMs. There are many papers that run very carefully designed tests, created by researchers that are working on these questions full-time and that are much more familiar with the technical details than your average blogger or YouTuber.